Hello there, I'm Kev Sheldrake. I'm going to be talking about HiTag2 RFID, which is low-frequency RFID cards with crypto handshakes and authentication and encryption. I was going to start by showing my lovely video, 44con Happiness, but I've wasted so much time setting up that you'll have to go and look for that on YouTube. So if you search YouTube for 44con Happiness, and you'll find a silly video I made a couple of years ago that I think is awesome. So, normal slide, this is a bit about me, it's the normal stuff you'd expect. I do work in cyber, clearly. So, the first question, of course, is why copy 125 kilohertz RFID tags? And the answer is because they're used to secure things that are quite high value assets. So, you find them in cars, protecting the immobilizers on a number of cars. You find the same crypto in use on the 433 megahertz flippers that open the doors. You find them in building access control. Now, I've not looked at cars, but the same technology and the same stuff would work in cars, apparently. You might need different antennas. I haven't even looked at keys. So if this doesn't work for you with your cars, then you might have to do a bit of hardware to make them work. But basically, yeah, people use them to secure things because they think they're secure, and obviously they're not. So I'll start quickly by talking about a simple RFID tag at 125 kilohertz. These are the ones you normally find when you're doing a normal building access control job. So EM4102s or Q5 or unique are kind of the names they go under. And they're basically a unique identifier that is preceded by a synchronization pattern. In fact, the synchronization pattern is usually a part of the unique identifier at a technical level, not that it really matters. When the tag's energized, it repeatedly sort of talks the unique identifier over and over and over again, and the reader that's energized the tag spots the synchronization pattern within that stream, and then just reads whatever comes after the synchronization pattern, and that's the number it then uses to make access control decisions. So, of course, they're really easy to copy. If you want to copy those, go on Amazon, buy a 4102 RFID copier, and it's £6 or £9 or something, and it's literally a push button, and you can copy those. There's other types of tags like T5557s, T5567s, T5577s, all kind of same technology. And again, you can buy copiers from Amazon, a little bit more expensive, but you can do so. Equally, you could use an RFIDler, which I'll be talking about in a minute, or Proxmark for similar kind of jobs. But they're very straightforward. They basically broadcast their data in public. And so if you can read that data, then you can write that to a new tag, and then you've got a copy of the tag. So no one should be using those for building access control. Everyone does. So avoid. So quickly at the electronic level, or the RF level, how a 125 kilohertz tag works. They have no batteries in them. I mean, I'm imagining everyone in the room kind of has some idea of what RFID is, but this is just the background. The reader emanates a field at 125 kilohertz. The tag itself energizes from the field power, and that's what acts as its power source, essentially. And then the tag modulates that field by damping its coil or not in a kind of binary pattern, which the reader can then pick up. Equally, if the reader wants to talk to the tag, like say you want to program the tag with a new data, then the reader can modulate the field itself, and the tag can pick up those modulations. So there'll be a little capacitor within it to cope with the field going on and off and stay powered up. So data modulation and encoding, I'm not going to talk about this in any depth whatsoever, but there's different types of modulation and there's different types of encoding. And if you start playing with RFID, you'll become very aware of these very quickly. Some are easy to use, some are not so easy to use, but you'll get used to this. If you get anywhere in the world of Proxmark or RFIDler, they've both got support forums. Everyone's talking about modulation and encoding. So what would we want from a secure 125 kilohertz tag? Well, we'd want two-way communications so that it set up some kind of encrypted channel with some kind of randomized authentication, randomized because we wouldn't want it to be replayable. We'd want authentication and encryption because we wouldn't want it to be copyable. So the idea being that if you got hold of someone's tag, you wouldn't be able to read it, you wouldn't be able to copy it. And if you could eavesdrop on that tag talking to a reader to open a door, then what you could eavesdrop wouldn't be enough in order to copy the tag. That's kind of what we'd expect. So today I'm going to talk about HiTag2 in password mode, very, very briefly because it's awful, and HiTag2 in crypto mode, which is the interesting one, and that's where the attacks are coming from. There's lots of things I won't be talking about, and I'm not going to go through them in any details, but if any of this is interesting to you, there's a workshop tomorrow at 9:30 in the morning. Steve Lord did laugh a lot when he told me it was at 9:30 in the morning, where I'll be doing 2 hours. I say workshop, it's a 2-hour lecture with interactive questions, okay? There's no like sit and do type stuff and do stuff. It's just like watch and listen and ask questions where it doesn't make sense. But if any of this is interesting, then you can ask questions at the workshop rather than here. If you've got questions about this bit, this kind of talk, obviously ask at the end is probably better. So there was an academic paper called Gone in 360 Seconds, Hijacking with HiTag2 by Vidal, Garcia and Balash. This is from 2012, and this is a seminal paper. If you look at the Proxmark forums or the RFiddler forums, there's a lot of people asking for implementations of these attacks because they let you start cars, essentially. I will say that the authors went on and last year produced a new paper called Lock It and Still Lose It, where they could do everything much faster, and that's the one they got sued by Volkswagen over. They actually wrote in their paper, we can open the doors and start up every Volkswagen from 1990 to 2016, which also means every Seat, every Skoda, and every whatever the other cars in Audi. They said, we don't know about Lamborghinis and Bugattis because no one will let us have one to try. But they theorized it would be possible. So, so Volkswagen took a great interest in their paper last year. And certain details didn't appear in the paper as a result. But I'm focusing on the one from 5 years ago. So HiTag2. HiTag2 is an RFID tag. I have one here. I mean, this is like in the ISO card format, but equally you can have little round tags. They all have 8 pages, and each page is 32 bits long. The first page is the user, or is the unique identifier for the tag, which is factory programmed and read-only. So when you buy yourself a HiTag2 tag, it will have a UID in page 0, and you can't change it. There are rumors of Chinese ones where you can change it, but I've never seen one personally. That UID is only used in the crypto handshake type stuff, or the handshaking. It's not used for access control decisions, and that's important because it's public data. That's why it's green. You'll see a color scheme appearing, but that's why it's green. The red pages contain the keys and passwords for the tag. That provides the security mechanisms. And then the pages 4 to 7 contain user data, which is 128 bits of information, which essentially makes up your person information. So when you go and turn up at a building and flash your card at it, that's the information it's going to make access control decisions based on. If we want to copy these, we need all of that. And obviously, that's where the fun bit comes in. In both password and crypto mode, they have pre-shared secrets. They have to, because there's there might be lots and lots of readers in an estate, because there might be lots of doors, and there might be lots and lots of tags in an estate, because there's lots of people. Well, the only way they can communicate securely is if they both know something that the other one knows. So it's shared secrets and mutual authentication throughout. So password mode, I said I'd talk about this very briefly. This is the protocol for HiTag2 password mode. As you can see, everything's in clear. That means if you can eavesdrop on the communications, which if it's your tag because you're an active insider or because you've stolen a tag or found a tag, then you can eavesdrop the information, and once you've got those passwords, you can then interrogate the tag directly yourself. So we're not going to talk about password mode again, but Proxmark and RFiddler can both eavesdrop on these things. Crypto mode, on the other hand, apart from the UID that's sent at the beginning in clear, because that kind of bootstraps the process, everything's encrypted afterwards. It sends the reader sends it a nonce, which is encrypted. It sends it a challenge response value, the challenge being FFFF, which gets encrypted and sent over. The tag can then sort of use the nonce to seed its RNG, decrypt the challenge response value, make sure it is FFFF, and then it can send back its page 3 page, which has got the config byte and the tag password, so the reader can confirm it's the right kind of tag from the right system, at which point the reader can then send commands and the tag can then respond, and all of that is encrypted. So in a nutshell, this is how it works from a very high level. The reader has the key, the tag has the key. The reader seeds its PRNG with the key and the nonce and the UID from the tag. It then encrypts the nonce and sends it to the tag. The tag seeds its RNG with the key, its UID, and the encrypted nonce that it's just received. And from that point onwards, the two PRNGs on the reader and the tag are both in step. They both seed to the same starting point, and as you extract bits from each of them, you'll get the same bits out of each end. So you can then use it as a stream cipher, or as the pad for a stream cipher. So stream ciphers, you all know about stream ciphers. It's that famous XOR thing. You basically take, if you've got a 32-bit message to send, you ask for 32 bits from your PRNG, you XOR that with your data, and that gives you encrypted data. And then at the other end gets 32 bits out of its PRNG, which will be the same 32 bits. It'll be the same key stream. They XOR that with the encrypted data, and that gives them back the plain text. And then the PRNGs are back in step again. And so it's quite straightforward how they can communicate. It's half duplex. It's like one talks and then the other one talks. So let's have a look at the PRNG, pseudo-random number generator, for those that are catching up. It's a linear feedback shift register. Now, if you're like me, you'll have no idea what this is before you come across it, but a linear feedback shift register is a very common way of implementing PRNGs. It's used all over the place. In fact, NASA uses LFSRs for various things. There's lots of different constructions, but this one's pretty straightforward. So it's 48 bits wide, and it's initially seeded with the UID and the lower 16 bits of the key. This will be on the reader and the tag at the start of this sort of handshake. At this point, the reader generates a new nonce that's 32 bits wide. It XORs that with the upper 32 bits of the key, and then it shifts that in to the LFSR. And as it shifts it in, the bits on the right fall out and disappear. And as it does it, for every bit it shifts in, it generates a bit of PRNG output, which will be a pseudo-random bit stream, essentially. So you're pushing in 32 bits, there'll be 32 bits of output coming out. It uses that 32 bits of output that's come out to XOR that with the nonce, which essentially is encrypting it in this stream cipher that we just talked about, and that gives you the encrypted nonce, which then becomes public data, because that's then transmitted to the tag as an encrypted value. The tag, and this bit's quite clever, I quite like this, it sets itself up in the same situation. It can get a bit out of the PRNG, because you get the bit before you shift the next one in. It's got the upper 32 bits of the key, and it's got the encrypted nonce that it's just received. Well, it basically XORs the first bit of that encrypted nonce with the first bit of the PRNG output and the lower of the last 32 bits of the key, and shifts that bit into the LFSR, which moves the whole thing along, which generates another bit of PRNG output, which you can then use to do the second bit. And then that, whatever the output is, that goes back in, and it can do the third bit. Well, the clever thing is, when it's done that, both the tag and the reader end up in exactly the same situation because of the magic of XOR. So this is now a fully seeded pseudo-random number generator LFSR. And as you can see, it's all red because these are values that we do not know as an outsider. We don't know what the key is, and we don't know what the nonce is. All we know is what the encrypted nonce is at this point, which, as you can see, is kind of lost in the world at this point. At this point, the feedback function is enabled, and so from now on, we've seeded the LFSR. Every time we generate a bit of output and shift the LFSR, we're not shifting in seeding information, we're shifting in a new bit, and that bit comes from the feedback function. So it now becomes autonomous, like any pseudo-random number generator. You seed it at the beginning, and then it just keeps on generating. Well, this is how it generates. So if we're encrypting data, as you can see, this is the stream cipher. You basically get as many bits out of it as you want, XOR that with your data, and that gives you encrypted data. And on the other end, you take your encrypted data, XOR that with the PRNG output, and that gives you back the original data. So we'll quick look at the feedback function. It is simply the XOR of 16 bits from the LFSR. I would say randomly chosen, but clearly not. Clearly, someone decided this and designed this thing. But it's 16 of those bits. And if we don't know the internal state of the LFSR, it'd be very hard to predict what those 16 bits are. When they're all XORed together, you get one bit. It's either a 0 or a 1. Your chances of guessing that without any information is 50-50, as it should be. Now, the output from the PRNG is not simply the bits that fall off the end when you push a new bit in. It's actually generated by a filter function, f. And that filter function is made up in a hierarchy of functions A, B, and C. And each of those functions take 4 bits from the LFSR. So you've got 48-bit state. We're going to pull 20 bits from that in chunks of 4. And they feed into these functions. Each of those produces 1 bit of output, which is 50-50 biased. And those 5 bits feed into function C, which produces 1 bit of output, again 50-50 biased, and that output bit becomes the output of the PRNG. So as you can see, it's kind of hard for us to predict what this PRNG is going to output, essentially. When you sort of start, you sort of think, oh, there's bound to be something really bad in the crypto, and there is, which you'll all be amazed by when we get to. But so far, this is looking pretty solid, I think. So right, we'll go back to the protocol. So it's sent the encrypted nonce. It's then sent the challenge response value encrypted. The tag's confirmed that. It's replied with its page 3 value, which is the config and the password, encrypted again. And then the reader gets to send commands, and the tag gets to respond to them. So let's talk about commands. There are 4 commands in HiTag2. They're all 5 bits long. So the first 2 bits determine which command it is. So you can read the page. You can read a page with all the bits inverted. You can write a page, and which will obviously require following data, what you want to write. And then there's a halt command to turn a tag off, which is useful in collision environments where you've got multiple tags. You talk to the one that's the loudest, and then you halt it at the end, and then you talk to the next one that's loudest. Apparently, not had it confirmed, but apparently they use this in Las Vegas to track chips in the gambling halls in the hotels. And so they can talk to hundreds of chips at once using this kind of protocol. So if you happen to know their HiTag2, who knows? Just saying. I'm not sure Vegas is the right place to get arrested, though. So if you imagine that a command is 5 bits long, you don't just send the 5-bit command. You actually send a 10-bit command, which is the 5-bit command followed by the inverted version of that 5-bit command, right, for integrity purposes. You don't want to ask it to read a page and accidentally what gets received is read page inverted and give you back the inverted version of the page, because that's not what you're expecting. Equally, you don't want to say read page and it sends you back write page. So they've got integrity built into the protocol, and that's basically just invert the 5 bits. So 1 to 0, 0 to 1, etc. Like not it, okay? But you don't only have to do it twice. You can do it as many times as you want. So as long as each block of 5 goes normal, then inverted, then normal, then inverted, then normal, then inverted, you can do this as many times as you like. Literally for thousands of bits if you wanted to. And the tag that receives this will check, after it's decrypted it, will check that each block is the inverse of the next block all the way along what it's just received to confirm that there's been no errors in transmission. It's a very strong integrity thing, something that we're going to abuse really badly in a second. So let's get on to some abuse. So the paper that I mentioned earlier, Gone in 360 Seconds, by Vidal, Garcia, and Balash, 3 attacks in that paper. And I'm going to talk about the first attack in this talk, and in the workshop tomorrow, I'm going to talk about attacks 2 and 3. I would have loved to have talked about all 3 in an hour, and as you'll see if you come to the workshop tomorrow, it just wasn't really feasible. Not in any kind of depth, not in the kind of depth that you'd like to see anyway. So we'll talk about the first one, which is a nonce replay and length extension for key stream recovery attack. I'm sure there's a paedophile joke in there, but I can't quite think what it is off the top of my head. Right, so obviously you'll have noticed from that protocol that we talked about earlier that the only entropy, given a particular tag, so if I've got a tag and it's got a particular UID on it, then as long as we're only talking to this one tag, the UID doesn't change, the key doesn't change because it's the same key on the entire system. So the only entropy in the system comes from the nonce that's generated by the reader. The tag itself generates no entropy. So that means if we capture the encrypted nonce and the encrypted challenge response value that's being sent from the reader to the tag at some point, then we can pretend to be the reader and replay that to the tag, and there'll be valid values. There'll be nothing wrong with those values, and the tag will quite happily respond to them. That will seed the PRNG on the tag to a particular point, which we don't know, and we don't know what that key stream is going to be that comes out of it. But what we can guarantee is that every time we initialize the tag with that particular encrypted nonce and challenge response value, the PRNG will go to the same place and start from the same point, and therefore have the same key stream coming out of it every time. So we're going to use that. This is the nonce replay side of it. What we're going to do is every time we try and do anything with the tag, we're going to start by initializing the tag with the same encrypted nonce. And that means we'll have the same key stream in every session. And obviously, anyone who knows anything about XOR and crypto means that you've now got something you can attack. So this is just to sort of say, remember after the nonce was sent and after the nonce was received by the tag, that was the state of the LFSR. As you can see, the only entropy is the nonce, the NR value. This is how we're going to emulate it. Basically, we're going to use, so I'll hold it up so you can see. This is an R fiddler. I guess everyone's seen one. It's like a Proxmark, but better for low frequency. So if you want to do, top tip, if you want to do 125 kilohertz RFID, use an R fiddler. They're only about £100 from Aperture Labs, and they are really good. If you want to do high frequency, use a Proxmark 3, because Adam Laurie, who wrote the code for this, wrote the code for a lot of the high frequency code for Proxmark, and that works. But the low frequency code for Proxmark, no idea who wrote that, but it crashes all the time, especially in the HiTag world. So we're going to use that as an emulated reader, and that's going to replay the same nonce every time we seed it. So as an example, if we gave it the encrypted nonce 4A85B2DF, then it would seed the PRNG, and it might produce the key stream 010110011001110, blah, 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 right? And every time we see the tag with that nonce, we're going to get that same key stream. Hence the thing that's what we're going to attack. So the way we're going to do this is we're going to find the encrypted read page 0 command. So we don't know the key stream, but we know there's a command out there which will be the encryption of read page 0. We're going to find that, and we're going to play that command, and it's going to give us the contents of page 0. The reason we're going for page 0 is because we already know the plain text of page 0, because that's the UID, which is presented at the beginning of the session. Okay, so we know the plain text for the command we're looking for, read page 0, and we know the answer plain text. And so if we can find the encrypted version of the command, and we can get the encrypted response, we've then got the encrypted versions of those. We can XOR them together. That'll give us the key stream, and then we've kind of won. Okay, so encrypted commands are 10 bits long, which means there's 1,024 potentials. Within there's 16 valid read commands, 8 for read normal and 8 for inverted pages. And when you send a valid encrypted read command, you get back a 32-bit response. But if you send an invalid command, you get back the unencrypted error response. And the reason it's unencrypted is because clearly your crypto has failed. If you ignore hackers and just think about the normal run of stuff, something's gone wrong in the process. Well, it can't reply with an encrypted value because there's no guarantee the crypto is set up correctly and that it can decrypt what you've sent. So the error is always unencrypted, and it's always that value there, F402889C. So we've now got a canary that we can compare against. So the approach we're going to take is we're going to find one valid encrypted read command, not know which one it is, but find one. We're going to bit flip that to find the other 15, and then we're going to test each one until we find the one that actually is read page 0. And then we're going to use that to recover the key stream, and from there we're going to attack the card. I'm going to go through all those in detail. So here would be the simple brute force approach to finding a valid command. You've got 1,024 of them. Just try every one after another. Make sure you seed the card before you send a command, and eventually you'll hit a valid one. That's quite lame, not very optimized. So a different way of doing it, if you imagine that we've got this encrypted command, which is going to be EFGHI, JKLMN, each of those is a single bit. We know that F will decrypt to 1 and K will decrypt to 0, because CM0 has to be a 1 for a read command, and the second half is the inverse of the first half, right? So we also know that, so F and K must decrypt to 1 and 0. We know that EG, H, and I must decrypt the inverse of what J, L, M, and N decrypt to. Well, if we don't care which read command we're looking for, we can hold J, L, M, and N to zeros, and that will decrypt to something, and then we can brute EG, H, and I to find the inverse of those when it gets decrypted. So we actually only need to brute force 6 bits, F and K, and EG, H, and I. So that gives us 6 bits, 64 possibilities, of which we're likely to get hit after 32. So we've just kind of reduced our problem from some 16 over 1,024 down to 32, whatever that is. But yeah, it's better. So we'd cycle through those until we found one encrypted read command that gives us back any value other than the error, right? and we'll call that EFGHIJKLMN because it's, easy. So what we're going to do now is we're going to find all the other valid read commands, and we're going to use a bit of magic. So if you remember, F decrypts to 1 and K decrypts to 0, and EGH and I decrypt to the inverse of what JLMNN decrypt to, then we can flip some bits. Because it's a stream cipher, if you flip a bit in the encrypted version, it flips the same bit in the plaintext version, right? That's Crypto 101. So if we had an encrypted command that happened to decrypt to read page 4 inverted, for example, right? And it happened to be this key stream, and it happened to be this encrypted command that we had. If we flip the first bit, which flips it from a read inverted to a read command, you can see that we don't have to know anything about the key stream or which command we've got. We just know that flipping the first bit will flip that command. But when we flip that first bit, we also have to flip the 6th bit, because whatever the first one is going to change to, the other one's got to change to the inverse of that. So if we flip a bit on the left side, we also have to flip the same bit on the right side. But we don't care that it's encrypted. It flips the plaintext bits as well. So we can flip the inverted bit quite happily. Equally, if you've got the page bits, which are the 2nd, 3rd, and 4th, the 3rd, 4th, and 5th bits on the left-hand side, and the 3rd, 4th, and 5th bits on the right-hand side, if it was read inverted page 4, we could flip the 5th bit, and it would change it to page 5. And equally, we have to flip the same bit in the right-hand side of the command as well. So it's the same thing. We're flipping bits in the encrypted content, and it's flipping the bits in the plaintext for us. It's like a known ciphertext attack. It's that kind of world. So using that, we can build up a massive table. There's only 4 bits to flip, and the same 4 bits in the right-hand side, which is 16 possibilities, which is the right number, 8 normal and 8 inverted. So we just build a big table that flips all of those. We don't have to send anything else to the tag. We can just, from getting one encrypted read command, we can then get the other 15 instantly. Well, instantly, it's a couple of lines of C, but so now you've got a table of all 16 read commands. One of those will be read page 0, not inverted, which is the one we're looking for, because we already know the answer to page 0, which is the UID. So what we're going to do is we're going to essentially test each one. That's really straightforward. And every time we test one, we'll initialize the tag so that we get the same key stream. Otherwise, none of this works, all bets are off. But we want the same key stream every time. So we're going to use our emulated reader. Remember, we're sending the same nonce each time, so we get the same key stream every time. So what we're going to do is if we take our first guess, we're going to assume it's correct, right? So we're going to assume our 10-bit guess, our first 10-bit encrypted command is read page 0, and we're going to assume the response we get back is the UID. So we can XOR the encrypted command that we send and the encrypted response we get back with the plaintext command for read page 0 and the plaintext response of what it should be, which is the UID, page 0. And that will give us the first 42 bits of key stream, if we're right. How do we know if we're right? Well, do you remember the extended command bit we had earlier? You can make your commands as long as you like. Well, we can make a 40-bit read page 0 command by basically just repeating the blocks. So there's 8 blocks. In here you can see you've got a normal block and an inverted block repeated 4 times, which makes 40 bits. So that would be a really high integrity read page 0 command, right? Well, we can reset the tag by reinitializing the PRNG again by doing the hello and here's our replayed nonce. So we're back to the same key stream we were using before. And then we can take our 40-bit read page 0 command, XOR that with the first 40 bits of the key stream that we think we've recovered, if we were right, and that will give us an encrypted read page 0 command. We then play that to the tag, having initialized the tag, and we either get back the error response, which means that it didn't decrypt properly, as in the integrity failed, and know that that isn't read page 0 that we've found, and move on to our next possible guess, or we get back a 32-bit response, which isn't the error. And if we get that, we know that that is the tag replying to read page 0. So that is the encrypted version of page 0, which we know. So we can XOR those together and get the next 32 bits of key stream. Right? It's a really neat attack. It made me think about crypto differently, the way these academics go about this. So at this point, we've got a replayable nonce challenge response pair where we can interrogate the tag. and we've got 72 bits of keystream, which is more than enough for what we want to try. So what we want to do is read all 8 pages. So basically, in a loop from 0 to 7, we basically initialize the tag with that replayed nonce. So we set the keystream to what we now know the keystream is. We make a command, read page n, or I in this case, and then we encrypt it. So we XOR that with the first 10 bits of the keystream, send it to the tag. The tag will quite happily say, yes, that's a valid command, that is this thing, and reply with an encrypted response. Well, we can XOR that with the next 32 bits of keystream that we've got, and that will give us back the clear text version of that page. So we're now communicating with the tag as if we knew the key, but we still don't know the key. All we've got is the keystream that the tag's using, because we've used the nonce replay and the integrity protection to ensure that. So it's quite a neat little trick. And because you do the whole thing in a loop, you only need the first 42 bits of keystream, because each time around you reinitialize and use the same bit of keystream again. So that should give us back all 8 pages of the tag. And you notice that the key is conveniently in pages 1 and 2, and the tag password is conveniently in page 3. So once you've got back your 8 pages, you can then write down the key, and from this point onwards, you can just auth to the tag by setting your own reader to use that key, and then you don't have to do any of this monkeying around. So you crack one tag in a system, you can then make a reader that can read anyone's tag. You only have to crack it once. You don't have to crack it every time. So, of course, if you're like me, you go to the rfiddler page and you download the source code, and then you download the build environment, which is mplab IDE for PIC32, which takes about 5 hours to install on Arch Linux. Who knows? There's the longest 5 hours of my life. And you find it's all in C. I don't know if you can see that, but that's some of my horrendous code. But it's all C. And you can find all the code you need within rfiddler. So in there, I've written like a transmit and receive function, but I basically just went mining like the rfiddler code and found commands that I liked, and then hoiked them in and hacked them until they worked. So all of this code is up. Well, it's all on a GitHub. Whether Adam's pushed the button and brought it into the main master, I don't know, but he's supposed to do it today. So today, tomorrow, next week, sometime. I'm seeing him next week actually at hardware.io. So if it's not up by next week, I'll make sure it is next week. Sorry? Yes, yeah. We've had disagreements over style, as you'd imagine. Mainly, I have no coding style, and Adam does. So here's the commands that I've added to rfiddler. 6 HiTag2 commands. Basically, the crack function, which is the attack I've just talked about. Keystream function, which retrieves keystream, which we need for attack 2. I'm talking about tomorrow. A HiTag2 reader, which actually will just, given a key, will just read tags quite happily. And if you give it S, it will store them in NVRAM. So you can power the rfiddler off a battery, so you don't need your laptop, and then you can just like sort of rip off people's tags. It just chucks them all into NVRAM. When you chuck it back into your computer, you can then list, count how many there are, and then list them out. And I've modified the sniff PWM function so to actually read the encrypted nonce and encrypted challenge response values that the reader presents to the tag. So again, you can power it, that all goes to NVRAM. So you can power your rfiddler and stick it on the reader and present a tag, and it will capture those values for you. So you've got some values to use in the attacks. So the way this attack would work very quickly is you set it to HiTag2 mode. You'd clear the PWM nonce storage, tell it to sniff as an auto-run command, which means you can power it from a battery, stick it on the antenna, collect a load of values, plug it into your computer, list the values you've got, and then use one of them in the attack against the same tag that you've just got a nonce for. Would you like to see a demo? So this is the live demo. There is no recording. I don't know if it's easier up here. Right, so this is rfiddler. It's all in Minicom. So there's all my new functions, shiny. So make it HiTag2. Right, I've got So I've got two R fiddlers up here. I've got another one acting like a reader. I will say, like, getting a HiTag2 reader is really hard. Like, I've got one for a build and access system, but it's not a normal one. It does other stuff that is far too complicated to talk about in these talks. But it's a slightly more involved protocol. But getting an actual HiTag2 reader, so Frosch makes them, and there's other people who make them. Tagnology box up one from a company called Frequent, and Tagnology, horrible to deal with. Like, just to say, like, I've tried to deal with them, not very nice people. And the Frosch one, I can't make any of them work. I've had 3 in my hands, and none of them work. So I'm using another R fiddler as a reader, using my HiTag2 reader command. So we're sniffing the PWM traffic, and you can see there the start auth command, because the reader's constantly start authing. And I put a tag on, hey, right, there you go. So you can sort of see it interacting, and you can see the nonce keeps changing, the PRN, yeah. So that would be how we'd capture the, oh, it goes off the side of the screen, that's a shame. The joys of live demos, eh? Right. Oops. Oh, sorry. Oh, I can't fucking type. I don't think that was on the mic, was it? Good. So use HiTag, right, okay, and then put a, come on, get the tag the right way around. Right. So yeah, so you can see the PRN is the encrypted nonce, and the secret is the encrypted challenge response value. If we were to then go, like, list the ones that we've got, look, I've got loads that I've just captured doing that. So you could take this and put it on the reader, and you could capture a challenge response, an encrypted nonce and a challenge response value. You probably want to capture a few, because if any of these bits have been flipped in the RF world, then they become useless to you. So get more than one, because you'll probably need them. Now, if, so I take my tag, we can take the last one. Yeah, I'm actually doing it live. I'm not even using my canned values. We take the last one. I've got a tag on there at the moment. Oops, sorry. No. Yep, there. Right. So we hit crack, and we give it the encrypted nonce, encrypted challenge response value. Okay, I need to move my laptop around a little bit. The field's not very, right. Oh, it worked. Okay. Let's just run that again and see if it works, like, properly. Now I've moved all the stuff out of the way. Yeah, this yeah, there. Oh, yeah, that's because it had hit a non-read command at that point. Yeah, so that's how the attack should look. Okay, so there you go. That is attack 1 working. And then we could. That's all 8 pages. Yeah. So can you see? Can everyone see? I can't even find my mouse. There's one. Can everyone see this? So that's the UID there, which is public. That is the the upper 32 bits of the key. That is the lower 16 bits of the key. That's the config byte and the tag password. And this is all data, user data. That's my office phone number if anyone cares. Because you have to put something in there, don't you? Right, so we could then go HiTag2 reader. So we could paste this in. So what, 5806. And oh, these are like test cards that I've made myself, as you can tell. They're not from any real system. So yeah, don't go writing that key down thinking it's going to get you in anywhere. But so that's reading tags now. If I grab the other tags, right, you can see there's a second tag, beef face, and there's a third tag, feed face. So, you know, as I say, the reader command is pretty straightforward. That's done that. That's done that. Right. I don't know how badly I'm doing for time. It's 3:15, and I finished at past. Is that right? Oh, wow. It's almost like I practiced this. Right, so once you've got the 8 pages of data, it's really easy to clone a tag, okay? Because we can either use HiTag2 reader, which I just demonstrated there, or you can take the 8 pages that you've got from the crack command and write them into the VTag. So a VTag on rfiddler is a virtual tag. So you tell it what type the virtual tag is, so set VTag, HiTag2, and it will create all the right space and structures for HiTag2, 8 pages. And then you can just rewrite 0 for bank 0, and then the bank 0 contents, rewrite 1 for bank 1, or if you want, you can go rewrite 0 and then all 8 banks, and it will just chuck the whole lot in. And once that's in the VTag, you can put a blank HiTag2 on the antenna and go clone, and then tell it the password or key of the blank, which is in the specification sheet for HiTag2 tags. I've got it in text files everywhere because I always forget it. It's like 494D, something or other. But it's MIKR in capitals in ASCII, essentially. But you can find it in the specification sheet. And so you need that in order to auth to a blank tag, because a blank tag already has a password on it, and it was already in password mode. But once you know it, it's dead easy. UID 0, you can't change page 0, but the page 0 UID value is only used to set up the crypto. It's not used for access control decisions, typically, because it's public. Why would you? And I say it can be done at distance with the right equipment. I would argue that technology using a frequent HGRM801 is not the right equipment, because the read range was only about 18 centimeters and the whole thing died. And we don't quite know why yet. We haven't done a full post-mortem. But that's probably not the right equipment. We have alternative ideas, and I'm going to talk about those in the workshop if anyone is interested in long-range HiTag2 reading. So if you cared and you wanted to copy someone's car keys, or you wanted to get access to a building that was using HiTag2, then you probably want a long-range reader as part of your snooping around, stealing things up, people realizing. You will have the same problem that we've had, and you've got to build something. All right, so it's not trivial, but with the right equipment or with a really good RF electrical engineer, you might be able to build the right thing. We're not really good RF electrical engineers, as you can probably tell. So closing remarks. This attack needs access to a tag. You do need a valid tag to do this attack, right? So you have to either be an insider and have one, or steal one, or borrow one, or be a contractor, or find one on the street, or something, right? You do need a tag. And you need one valid encrypted nonce, encrypted channel response value. But that's easy. Once you've got the tag, you just go to any reader, stick the rfiddler on it, wipe your path, and you'll get the nonces. As you saw, it takes literally seconds to crack a card, which I think is awesome. Now, you can, it's recommended in the tag specification to read protect pages 1, 2, and 3, right, which contains the key and the tag password. And that's basically a config byte setting. And if you do that, then even with the key or the key stream, you can't read pages 1, 2, and 3. So you can get the user data, but you won't be able to copy the tag because you won't know what those keys are. Well, attacks 2 and 3, which I'm talking about tomorrow at 9:30 in the morning, honestly, crypto in the morning, 2 hours of crypto, you know it makes sense, right? I don't know what state you'll be in, but I will not be in a fit state to be talking maths. But that will recover the key using different techniques, and they're both awesome. They both build they build on this, and they're different to this. But if you like novel kind of crypto attacks, I think they're pretty amazing. So that is it. Does anyone have any questions?